Picking up from the previous lesson, so galvanization is a way of trying to prevent corrosion or trying to slow down corrosion. And when we say some material is galvanized, meaning to say it is coated with a protective layer of zinc so that corrosion or rusting is being slowed down. And it is in the electroplating industry where we can see this process in which corrosion resistance is the main goal and metal coatings on objects is the way to achieve this goal. Okay, so for example, you have galvanized square steel. So steel is an alloy. When we say alloy, it is a mixture. So alloy refers to mixture of metals. So it is a mixture of metals to improve property or properties. So the reason why alloys are made or alloying is being done, it's to improve the properties, or it could be improve the quality of different materials, especially metals. So steel is an alloy of iron and carbon. And when we say galvanized steel, so that alloy is being coated with a protective layer of zinc. So that is the very basic example where we can find galvanization. Okay. Now, in the previous lesson, we are able to consider measuring the voltage of a system, your electrochemical cell, in standard conditions. So previously, the different conditions we considered was that you have 1 molar concentration of solutions and gases are at 1 atmosphere. Okay, so this is the partial pressure of the gas. However, in reality, we cannot expect standard conditions at all times. Meaning to say there is always a slight deviation, or there is always room for deviation. Okay, and so that's why we can calculate voltage in non-standard conditions using Nernst equation, and this describes the dependency of an electrode's potential E and the activities of the redox reactions species. So what are these species? These are your products and reactants. Okay, now one reason you might wonder, why do we always consider standard solutions or conditions? Okay, why do we consider standard conditions as basis for computation? Okay, that's because we aim to simplify for any process. We aim to have simplified calculations. That's why, even though in real life there is no such thing as standard conditions always, we can have basis. So that's simplify our calculations. Okay, so Nernst equation proponent is Walther Nernst. So this guy here, so describes the dependency of electrode's potential E. Alright, this is how your Nernst equation looks like. And if you look at, so one variable here is from the previous lesson, the standard cell potential, or cell potential in standard conditions, E naught. Okay, so Nernst equation is E is equal to E naught minus R This is the universal gas constant, and in SI units, it has units of joule per mole Kelvin, and it has a value of 8.314 times the temperature in Kelvin. Standard temperature, that is 298.15 Kelvin. So you do the math how much it is in Celsius, and then denominator n, this refers to the number of electrons transferred in the redox reaction. Your reaction is your basis, balance equation is your basis, times F, which is Faraday's constant, with units joule per mole volts, and then the value we'll use is 96,485, although there are different sources which has rounded up to 96,500. Some references use this value. Okay, and in terms of conversion or in equivalency of units, 1 joule is actually 1 coulomb per volt. Okay, and the reason why here, take note, this whole term here, this term here, is multiplied to natural log ln of Q. Now, how does this differ from the equation in the right side? So we have here the value 2.303 if we consider the logarithm of Q, wherein 2.303 is the natural log of 10, because we know that log here, this is base 10. Okay, this is base 10. Okay, meanwhile here, this is natural logarithm, so we don't have the somewhat corrective value. Okay, but if we use either of these, then we are expected to get the same answer. Now, what is Q, by the way? Q is the reaction quotient. Where can we find this value? First off, we consider your balanced equation because it's a redox reaction. So recalling, we have your redox reaction comprised of the reduction half reaction and the oxidation half reaction. And whenever we already balance the number of electrons being transferred, we can eliminate the electrons in the final equation. So we have a generic form of equation like this, okay, wherein the small a, b, c, and d refers to stoichiometric coefficients. So that is obtained from balancing. And then A, B, C, and D. Okay, so A and B are your reactants, C and D are your products. And then reaction quotient can be obtained by the following. So Q equals, we notice we have brackets. So if you have brackets, that refers to concentration, and it is usually given. Otherwise, it is assumed to be standard, which is 1 molar. But in non-standard conditions, it is given or stated in the problem. Now, the concentration of, say for example, your product C, you raise that to the power of whatever stoichiometric coefficient you have, times the concentration of product D raised to the stoichiometric coefficient all over. Now we consider the concentration of reactant A raised to coefficient times reactant B raised to the coefficient. Another form, or sometimes you're dealing with gases, so you have to consider the partial pressure. So here, this is supposed to be partial pressure. So this is partial pressure. Or sometimes pressure is the term being used. Okay, so same, partial pressure of product C raised to the coefficient times partial pressure of product D raised to coefficient all over the product of the partial pressure raised to the respective coefficient of A and B. Alright? So, these coefficients simply tell you that you really need to balance the equation first. Now, another parameter introduced is F, or the value of Faraday's constant. It is a physical constant defined as the quotient of the total electric charge Q by the amount, so N, of elementary charge carriers in any given sample of matter, where the Faraday's constant F is equal to total electric charge divided by number of, so for this case, electrons, so Q over N. Now going back, so from there, so from our equation, so initially we have there, so going back, we have RT over NF. So this is RT over NF ln Q. And then the other one, you have E equals E naught minus 2.303 RT over NF log Q. And what were the conditions? Right, so we have here R, let me move here. R is equal to 8.314 joule per mole Kelvin. Okay, so let me rewrite this again. Then we also have a temperature 298.15 Kelvin. Faraday's constant 96,485. What was the unit? So we have joule per mole volts. Or we know this is 1 joule is 1 coulomb volt. So let's have the conversion there. What else? So N. Okay, so N is not dependent on the balance equation. So how did this term become this one, 0.0257? So this is units volts. Yun sa pagka 0.0257. We simply plug in these values. So from here, our equation becomes E naught minus 8.314 joule per mole Kelvin times, we have here 298.15 Kelvin all over N times 96,485 joule per mole volts. Okay, I hope you can see the outcome. Let me align this. Now simplify. Okay, so we have here, if we are to plug in the value, so let's try to use our calculators. So do it on your own and try to see if we can get 0.0257. So we have 8.314 times 298.15 divided by 96,485. So you should get approximately 0.02569 or 257. Now this is all over N. And then, in terms of units, let's cancel units. We can cancel Kelvin, then joules, and mole. Now you have here per volt. So volt is left in the denominator. So this will be volt V. And then we have ln of Q. So try this. So try this one here and see if you can get the same result. Only that this time the starting equation is E is equal to E naught minus 2.303 RT over NF log Q. Okay, so do it as an exercise. So derive this one. Okay, that's for your exercise. So that's where our Nernst equation is derived. Let's have a sample problem. Assume that you have a cell that has an iron 3 concentration of 0.015 molar and an H plus or hydrogen ion concentration of 1 times 10 to the negative 3 molar. The cell temperature is 38 degrees Celsius and the pressure of hydrogen gas is maintained at 0.04 atmosphere. You are given here the half reaction and the standard cell potential of each, and recalling from the previous discussion, so the standard hydrogen electrode has a standard cell potential of 0. Alright, so 1, what are the half reactions? You have to identify which one is reduction, which one is oxidation, and what is the overall reaction, overall balanced equation of the reaction. And then what is the standard potential? So you're given the data here, so you can definitely get that one. And 3, what would the cell potential be under the specified conditions? So this time we'll be able to get the specified cell potential using this data, wherein you're given concentration of the solutions and partial pressure of hydrogen gas as well as temperature. So let's start. Let's consider first the half reactions. Now, by determining which one is the reduction and oxidation half reaction, then we can determine the standard cell potential. Now, looking at our equation, so which do you think is oxidation? And which do you think is reduction? Okay, so since we have here the more negative is iron, diba? In the previous discussion, the more positive is the cathode. And because here, the more negative is iron half reaction, so I mean to say this is found in the anode. So this is oxidation. Right? Leaving us here, this occurs at the cathode, and this is reduction. Okay, so what will we do with this? We will flip. So for number 1, let's have your oxidation. This is iron solid forming iron 2 plus iron 2 plus 2 electrons, and our standard is now positive 0.44 volts. And reduction, so we have here, copy the whole equation. Forming hydrogen gas. and our standard, so this is 0. Alright, let's get the overall reaction. Sorry, dili straight. So we can see that we have equal number of electrons. So our overall reaction, we have iron, okay, plus hydrogen ion forming iron 2 plus hydrogen gas. This is your overall reaction. For number 2, we have here standard cell potential. Recalling cell potential of the cell potential standard, we have the reduction plus oxidation. Okay, and since one of them is 0, so we know that the standard cell potential is 0.44 volts. So this is oxidation, this is reduction, and this is that of the cell. So this is for number 2. Alright, this is for number 2. Number 3. What would the cell potential be under the specified conditions? This time we will consider the concentration and the pressure, partial pressure. So let's rewrite our equation. Nernst equation, E is equal to E naught minus, so let's try 0.0257 volts all over N ln Q. Right, since we are required to use the reaction quotient, let's determine Q first. So here we have to consider the states of each of the species, each of the reactant, each of the product. Looking at our equation, we can see iron. So this is A, this is B, and then this is C, D. By the way, here in this equation, this simply represents reversible reaction. Alright, so it can proceed forward, can proceed backward. So that's the meaning of this double two-way arrow, reversible reaction. Alright, so here we have to get the, or assess, balanced ba in terms of molecular. So 1 iron, 2 hydrogen, 2 hydrogen. So A, B, C, D. So A, so here small a is 1, small b is 2, that's the coefficient. Small c is 1, small d is also 1. But since iron is solid, so this is excluded. Okay, so that's because another rule in reaction quotient is that only gases and aqueous solutions must be considered or must be included. Okay, so here iron is solid, so this is excluded. So we will not include it in our reaction quotient. Alright? So this time, let's write our equation. Q is equal to, so what will be our numerator? So this will be C. Alright? So concentration of iron 2 is said to be 0.015. Did I say iron 3 earlier? I think so. Sorry, this is iron 2. So concentration of C is 0.015 molar times partial pressure. So since this is a gas, so we're given partial pressure of 0.04 atmosphere. Now, in terms of exponent, C is 1, D is 1. So you may write here 1, there's a delay, right? That's understood as 1. All over, A is excluded. So we have here concentration of hydrogen ion. So we have 1 times 10 to the negative 3 molar, then squared. So this is our Q. This is how our reaction quotient looks like. Now, let's calculate now the cell potential. So E, so we will plug this in here. So cell potential E is equal to E naught from number 2, that's 0.44 volts, minus 0.0257 volts, all over. We go back to our equation. So N is equal to 2. So this is 2 electrons times ln of this whole term. So this is ln of 0.015 moles times 0.04 atmospheres all over 1.0 times 10 to the negative 3 molar squared. Alright, so this is now our equation, Nernst equation, to find the cell potential given the specified conditions. So how much is our cell potential for the specified conditions? Right, so let's have a calculator. Alright, and then let's see, okay, so how much it is. So we have here, if we try to get the value, so on your end, so how much is this? So this should give you a value of around 0.3569 or 0.357, I think, volts. So this is the cell potential under specified condition, and this one is standard. What have you noticed? Alright, there is a difference. So this is standard, this is non-standard. Alright, so as the label suggests, so the standard is often greater than the non-standard. Alright, so that's for cell voltage under non-standard conditions.